Okay, here in this presentation, we'll be looking at some very basic concept of permeability and seepage first. Thereafter, we will be discussing one case study. I'm not very sure about the ratio of the audience, how many of you have work experience, how many of your students. So, but for very fresh grads or probably undergrad students who are currently doing their bachelors, some of the terminologies may not be very familiar. However, as we go, I'll try to discuss how much ever we can on the go. As I mentioned, we'll be just looking at some very basic ideas, for the benefit of everyone. Some brushing up of some basic concepts first. Okay, so here we can see a picture of ground soil. So once you have a close look at it, what we can see is that soil comprises soil particles, which are solid particles. At the same time, it has got voids in between these particles, right? So that's an illustration on the right side. And these soil voids are interconnected within the soil. I'm pretty sure we all have heard of groundwater table, right? So that is there is presence of water beneath soil. So we won't be discussing about different types of groundwater table or on groundwater table extensively here. However, groundwater table can be as shallow as zero point 0.5 meters to many, many meters, depending on various factors and terrains in different countries. So, for instance, I've been working in Singapore for quite some time. So here in Singapore, it's like about it can be as shallow as 1 meter below ground up to 3 to 4 to 5 meters, and some mountainous areas it can be much deeper. So below the groundwater table, the void within the soil will be occupied by water. This is called pore water. Okay, this water is called pore water, and this water within the pores induce pressure on these solid particles, which we call pore water pressure. I'm pretty sure most of us are familiar with this term. Here on the slide on the left, we see those. These are two, just simple two illustrations of soils of different particle sizes. On the left, we have bigger particle size, and on the right, we have soil of smaller particle size. So the soils with bigger particles have bigger voids and better void interconnectivity, as we can see in the illustration. Whereas the low permeability soils have smaller particles with much smaller voids and hence may not be well connected as it is in case of high permeability soil. So permeability is to speak about is the ease with which the water can flow through the soil particles. When it comes to soil mechanics, that is permeability, the ease with which water can flow, maneuver through these voids. So when we are talking about seepage and permeability, we should be aware of two very basic concepts of fluid mechanics. So just to refresh, on a very, very superficial level, we will talk about Bernoulli's theorem and Darcy's law. In Bernoulli's theorem, it defines on how to estimate the fluid energy. So energy that is retained within fluid particles are contributed by three different components: velocity component, the pressure component, and the position of the fluid particle. So this is basically the potential energy. Let's look at this simple illustration. It's an illustration of a gravity dam. We have water at a higher level on one side and at a lower level on the other side. So let's hypothetically assume that a flow line from point A to point B, and just assume that there's a fluid particle at point X. Okay, so the total energy of that fluid particle at that point X, if you want to calculate that, it will consist of velocity component, pressure component, and elevation component, as we just mentioned. And fluid energy is generally expressed in terms of unit of length, and we call that as head. So it's velocity head, pressure head, and elevation head. So for water flow through the soil, that velocity head part is pretty insignificant and it's very small in number, and so we don't usually estimate that, we don't usually calculate that. So the total head, so for instance at point X, okay, the total head will be the pressure component due to, the energy component due to the pressure, which is the pressure head, and the next component is the elevation head. So for water flow through the soils, that pressure head is calculated as pore water pressure divided by unit weight of water, which is typically about 10 kilonewton per meter cube. So on the right side here, I hope you can see my cursor also, that you can see that pore water pressure is in kilopascal. I'm just for showing you, citing you the example on how we get the unit in meters. for water pressure is in kilopascals, which is kilonewton per meter square, divided by the unit weight, which is gamma W. The unit in SI will be kilonewton per meter cube. And by cancellation, ultimately, we get the unit to be in meters, which is a unit of length. So pressure head and elevation head will be in unit of length, and hence the total head or the total energy for water flow is mentioned in terms of length. And the elevation head for that fluid particle at point X is the height of that particle with reference to some datum. Datum is just a reference level which we assume during our estimation. Another concept that is described by Bernoulli's theorem is hydraulic gradient, which is denoted by letter I, small letter I. So this hydraulic gradient I between the streamline point A and B is equal to the total head that we calculated at A, like how we calculated in the previous slide, and the total head calculated at B. We subtract that and find the difference of these two heads, and then we divide it by the streamline length of A to B. So basically, the hydraulic gradient between any 2 points is the total head loss per unit length. Okay, now let's talk about Darcy's law. So Darcy's law states that velocity of fluid flow is directly proportional to the hydraulic gradient. Hydraulic gradient we just discussed in the previous slide, and hydraulic gradient does not have any unit because the numerator and denominator both are in length, so it does not have a unit. So velocity of flow is directly proportional to hydraulic gradient, is what is stated by Darcy's law. So in order to equate the velocity of the fluid flow to hydraulic gradient, we have to multiply that with a constant, right? So that constant, K, which was used here, is the permeability. So this is the term that we are interested in for this particular presentation. Okay. So as I mentioned, hydraulic gradient does not have a unit. K, permeability, K, the unit of permeability, same as that of velocity. Typically, we talk in terms of meters per second. So this is about, very, very basic idea of what is permeability and what is the relevance of permeability in terms of soil mechanics. If you're more interested to know about the details, because there are a lot of differential equations and which leads to all these theorems and all that. If you're interested, you can find them in any of the textbooks, any good textbook, but we're not going into that. The typical values of soil permeability are as given here. So as we can see, gravel, which has got bigger particle size than sand, has permeability value higher. So gravel has, if you look at this chart, you can see that gravel has got the highest permeability value, then the lowest for the clay. So as I mentioned, permeability is the ease with which water can flow through the particles. So permeability value, the K value is high, means it's easier for the water to flow through. So in gravel, which is a highly permeable material, it's easier for the water to flow through. Okay, now, as I mentioned, after just touching upon the very, very basics of permeability, we talk about a case study. Before that, here in the slide, you can see that we're going to talk about a case study on seepage induced slope failure. So seepage is basically, like any fluid, it has got a tendency to flow from higher level to a lower level, right? So what does it mean by a higher level? A point at higher level means it has got higher total head, and a point at lower level means it has got a lower total head, lower energy. So it moves, the water has got a tendency to move from a higher head to lower head. So that flow is what we call as seepage flow. So here in this case, we discuss about one specific project where a slope failure is, shown due to the seepage flow under heavy rainwater. And this particular case study was presented in Seattle at ASTM conference. ASTM stands for American Society of Testing of Materials. So here, when we discuss, we'll be going through the introduction of the project, and then we talk about what might have caused the failure of the slope. Then, some site investigations which was carried out to identify the issue. Then some failure analysis done, some simple one-dimensional failure analysis done. Then how a stable slope was redesigned based on the lessons learned from the failure analysis. Then we'll go through some parametric study of the influence of something called subsoil pipe installation depth. We'll talk about it. What is subsoil pipe? Then we just touch upon the how that failed slope was repaired and the construction sequence and all that. With that, we conclude. And also, I'll be going through some pictures taken from the site. Okay, so this is, you can see a slope there. You can find a lot of cracks here. We'll be looking at these pictures again, but this is the place where I'm talking about. So this particular site, was actually for a turf club, horse race club. And so they were doing this landscaping and the area for the horse racing and all that. So a very high hill, which was about 15 to 20 meter, it was cut. So this is the actual level of the ground, and it was cut to form this slope. For this particular project, the slope was longitudinally like 70 meters in length. So the 70-meter slope with a gradient of 1 vertical is to 2 horizontal. Okay, sorry, there is a typo error here. This is actually 1 vertical. If you're looking at the cross section of the slope, if I cut a section here, this is how it will look like. This is not 1H, it is 1V. So 1 vertical and 2 horizontal. So with that, we get this angle of the slope to be about 26.5 degrees. So this slope was cut in medium stiff residual soils. So I'll be touching upon what is residual soil for those who are not aware. And so what happened was, while they were constructing this, when they cut the slope and when they were doing all the activities over the site, there was this intense torrential rainfall within the site. So after a period of this intense rainfall, there was slip failure which occurred on site. So there was some kind of, just causes dish-like failure for a stretch of about 30 meters. And the depth of that dish, which if you can imagine, probably on a cross section, it was like, failing like a dish here. Okay. So that was, the depth was about 1 to 1.5 meters. When this failure occurred of 1 meter, 1.5 meter depth, and it was it was going backwards towards the crest of the slope. So they were not able to control that failure. So when they were trying to repair it using those dry cut fill from the same site, just put it back and dump it and compact it and put it back, it failed again. So what could be the possible causes of failure? So the presenters of this is actually one of my professors. So according to him, the possible causes of failure could be any of these three, or it could be a combination of the three. So to talk about the overburden stress relief, like large overburden stress relief by cutting slope and hence, the removal of the soil. So basically, when you remove soil from the initial position, the soil is experiencing a release of weight from the top of it, right? So that's called overburden stress relief. Here in this case, the ground was cut in like 15 to 20 meters depth of hill, as I previously mentioned, causing this unloading situation. And over time, the ground adjusts this loss of overburden and strength decreases, especially for cut slopes. And the second possibility of which caused the failure could be rise in groundwater table due to the intense rainfall, as I mentioned. And how this groundwater table would have risen. So we have a slope, which is called a crest. So water falls onto the crest, and from that crest, the water, seeps to the face of the slope. So basically, the face of the slope will be completely drenched in water, and it will not be, at the end of the day, able to sustain its own weight, and it drives down and causes the failure. And the third is insufficient subsoil drainage. So in case of slope, one of the important things that we need is we have to ensure that the slope surface, we should not allow the water table to reach closer to the face of the slope. This might cause a failure of the slope. So in order to avoid that, we should install subsoil drainage pipes so that the water doesn't reach the face of the slope, but just goes through these pipes and flows out. So then when this failure and everything happened, we need to find a solution, right? So the first step was to identify, to do some site investigation after the failure happened. To understand what is causing this failure, we should know, as I previously mentioned in the previous slide, one of the reasons could be, or probably the primary reason is the changes in the groundwater table. So to understand that well, three water standpipes were installed, which are P1, P2, and P3. So for those of you who don't know what is water standpipe, it's an instrumentation method which we do on site in order to see what is the level of groundwater table at different locations of the site. So three water standpipes were installed at the location, as you see, P1, which is closer to the toe, P2, which is at the middle of the face of the slope, and P3, which is closer to the crest of the slope. So from the water standpipe data, it was identified a probable, you can see a dashed line here, right? So that probable, this was identified as a probable groundwater table black line, which I'm showing with my cursor. So this one was, as I mentioned, it's like it was about 1 to 1.5. Some places, I think more than 1.5 meters. This was identified based on visual observation from the site. So as we can see, the probable groundwater table and slip plane both are very close to each other. So this formula that you see on the slide is this is just a one-dimensional infinite slope theory, which you may find in various textbooks. It could be this formula, or you can find other formulas as well, similar ones. So as I mentioned, for the benefit of those who are not fully aware of how slope stability works, FS stands for safety factor. So safety factor is basically a ratio between the resistance that the soil offers to the failure and the driving force which causes the failure. So ideally, that safety factor, or FS, has to be greater than or equal to 1. Ideally, it has to be slightly greater than 1 for the slope to be stable. And again, for the C prime, you can find a component called C prime here. This is cohesion. This is angle of internal friction. These two are the components which determines the strength of the soil. So for instance, for clay soil, most of the strength comes from the cohesion component. For sand and gravel, the strength is from the angle of friction, this phi prime. And beta in this particular formula is the slope angle. So as we discussed previously, for this particular slope, the slope angle is about 26.5, because it is a 1:2 slope. And H is the depth of the slip surface, which is this one. And small h, which we can see here, is the height of the groundwater table from the slip surface. This controls the pore water pressure on the failure surface. Yeah, gamma is the unit weight of the soil, and gamma W is the unit weight of the water, which, as we previously mentioned, it is typically about 10 kilonewton per meter cube.